Perfect.
Okay. Okay, so the last talk of this session will be given by Joffrey on two-way collaboration between flow and proof in Spark. Go ahead.
Thank you. Thank you for having me. So hello everyone, I'm Joffrey Huguet, and today I will present joint work with my colleagues Claire Dross and Johannes Kanig. The title of the paper is Two-way collaboration between flow and proof in Spark. So there are various kinds of static and dynamic verification frameworks and tools, all with their weaknesses and strengths. And it's common to try to combine them, either manually or automatically, and trying to integrate different analyses in the same tool. Spark is a tool to verify programs written in the Ada language. It combines two analyses working as different paths. So there is data and information flow analysis and deductive verification. And in this talk, I will present these analyses and their collaboration. As Spark is focused on verifying Ada programs, I will do a quick presentation of Ada first. So Ada is a general purpose imperative language. Its first version dates from 1983, and throughout the years, new versions of the language have been released. The latest dates from 2022. It allows for low-level programming, but also offers higher-level features such as object-oriented programming and concurrency. As Ada is designed for safety-critical applications, it inserts language-mandated runtime checks. These ensure that nothing can go wrong, and we'll talk about that just later. And at runtime, in case of failure, they lead to exceptions. So for example, here, we have an integer y, and we are trying to assign it x divided by c. We have a runtime check checking that c is not equal to 0. When accessing an array component, like for z, we have a check to verify that the index is in the correct range. Ada has strong typing and also enables the user to define new types and subtypes with precise constraints. These constraints are also checked at runtime. So, for example, here we have a small int derived from an integer, which ranges from -100 to 100. When a user attempts to assign it, Ada inserts a check to verify that it's in the correct range. In Ada 2012, has been added contract-based programming to Ada. It allows to annotate subprograms. So subprograms in Ada include functions and procedures. Procedures are just functions that do not return a value. We can see that parameters have modes. So by default, the mode is in, which means that the value can be read. Here, x is an in-out integer, which means that it can be read and assigned. So we can annotate pre- and post-conditions on subprograms. So the precondition here states that x should be strictly less than the last integer, and the post-condition states that x is strictly greater than the value at the beginning of the call. Another example of contracts are strong and weak invariants on types. So here we have a sorted array, which derives from an array, and the predicate states that it's always sorted. With a compilation switch, it's possible to evaluate this contract at runtime. So an exception is raised in case of an evaluation to false. Spark attempts to verify Ada programs. So it does so statically without running the program, does so for all inputs of the subprograms. It provides a sound non-complete analysis, so it might have false positives. So first, it tries to prove language-mandated runtime checks, such as the range check or the index check that we've seen earlier, as well as the user-supplied contracts. So when calling a procedure here, increment, it will try to prove the precondition. When assigning a value to a type with a predicate, it will try to prove the predicate on the value. So in this presentation, we're going to look at the two analyses performed by the Spark tool. The data information flow analysis that we call flow, and deductive verification that we will call proof. I will present them and share how the verification objectives are shared between the two so that each works at its strengths. The initial architecture is in black. Then I will explain the mechanism that have been put in place to improve the overall effectiveness of the tool by increasing the collaboration between the analyses. So on the one hand, flow, which runs first, computes information necessary for proof. So that's in red and the dashed line on the picture. On the other hand, some value-dependent checks are automatically deferred to proof to improve precision, as can be seen in yellow, the dashed dotted line. Finally, I will present a feature for which the handover from flow to proof can be requested on a case-by-case basis by the user. It's called relaxed initialization. So we'll start with the analysis that runs first in the tool, flow analysis. So flow analysis tracks flow of information between objects to detect dependencies. So it's based on the control flow graph of the program. It has the particularity of being fast and interprocedural, so it can see the whole program. But sometimes it's imprecise because it's not value dependent. So for example, here we have an example where all possible values of x are covered by the if conditions, but flow is not able to determine that sign is always initialized because there is a third hidden path, which is the else branch. Flow verifies contracts related to the program data flow. So here we have the set of global variables accessed by the subprogram, the dependencies between the inputs and the outputs of the subprogram, as well as the potential termination of the subprogram. So in the example here, we have the procedure add v to g, which will update the value of a global variable g depending on its initial value and the value of v. Flow is able to prove that all the contracts are correct. For formal verification to be tractable, we need simplifying assumptions. They have two purposes. The first is to reduce the annotation burden on the user. And second, they improve the automated provability. One of these assumptions is a strict initialization policy that's checked by flow. So this strict initialization policy states that all inputs of the subprogram are entirely initialized before the call. So in the example here, in the procedure P, it's allowed to read X because it's an input of the subprogram. So as such, it's allowed to read it. However, it also states that all outputs are entirely initialized after the call. So given that flow analysis is not value dependent, it's not able to determine that sign is always initialized after the call. This has a benefit of not needing user-supplied initialization contracts, which can be very cumbersome to write. So now we've seen that flow analysis is a non-value dependent interprocedural analysis. It verifies contracts related to the program data flow, as well as assumptions like initialization. Let's move on to the second analysis in Spark, proof. So proof is called deductive verification. It takes AdaCore annotated with contracts. From it, it produces logical formulas called verification conditions. These are sent to automatic solvers, so in our case, SMT solvers, and that verify them. And if all conditions are verified, the program and its contracts are correct. Because contracts are part of the Ada language, it means in particular that they follow the semantics of Ada. Regular Ada functions can be called inside contracts. They can have preconditions, so they might not be defined on all values. They can access global data and even modify it. And also they can potentially not terminate. These functions are mapped to logical mathematical functions in the underlying logic. These have the property of being total and described either directly, so for example, x gives x plus 1, or using axioms. In Spark, we have made the choice of not identifying logic functions, so all functions can be used. We have some conditions for that. They should not have side effects, and they should terminate on all inputs. They are translated to axioms, so that is, for all inputs satisfying the precondition, the result of the logic function satisfies the postcondition. But when we add axioms, when we introduce axioms in Spark, we do it with care, because if you are introducing an axiom who can be equivalent to false, you might be to prove anything afterwards. Such axioms are necessarily sound, provided the function terminates first, and second, the return value satisfies the postcondition. So here we have an example of a bad function whose postcondition is false. If we had to introduce the axiom for this one, it would translate as for all natural false. So this is an unsound axiom. Fortunately, while proving bad, Spark will check that there is no possibility for a return value to satisfy the postcondition. So we keep a sound analysis. Now we've seen flow that's fast but imprecise, and proof that's modular but more precise but slower. Proof checks everything that's not checked by flow, so absence of runtime errors and pre and post contracts. Now let's see how they collaborate. So first, flow computes information that's used afterwards by proof. So we've seen global contracts. The problem with the global contracts is that they grow with the call graph. So in particular, this means that they can be very difficult to maintain while you're extending your program. And second, they might not be interesting for the user. For example, the user just wants to verify absence of runtime errors. But these contracts are needed by proof. First, for precision, because the proof needs to know which data is modified by a call. Also, it needs this to be precise, because functions can read global variables, and they need to be treated as inputs of the subprogram. In the example, flow analysis computes an over-approximation of the global contracts, so that it produces the contracts for add v2g and read g. So, and in this way, proof later is able to show that the value of v was not modified by the call to add v2g, and the read value of g after the call is not the same as the one before. Another contract that can be generated by flow analysis are termination contracts. In general, Spark is only interested in partial correctness. That is, post-condition need only be valid if the subprogram terminates. But we've seen that non-termination can lead to unrealizable contracts, so unsound, that could introduce unsound axioms. So functions used in logic must terminate. Once again, flow analysis computes an over-approximation and checks termination of functions. So if we add a body to bad and we call a never-ending subprogram, proof is able to prove the post-condition because it's never reached, but flow analysis will complain that the subprogram might not terminate. Something linked to termination is recursivity. Recursion in ADA is not explicit, and moreover, it can even occur across different compilation units. But when verifying recursive subprograms, in particular logic functions, proof needs to make sure that the axiom introduced for the contract is not used to prove itself. Flow analysis, in this case, is able to compute a call graph. And if we take the bad example, we imagine that it terminates, and we add a recursive call in the post condition. If we added the axiom of bad, it would allow to prove the post, because it would state that for all natural, false. But when detecting recursivity, proof removes the axioms so that the axiom is not used to prove the post condition of the same axiom. So let's go back to the graph. Previously, we've seen that flow and proof run as separate analyses. And in this part, we've seen that flow is also used to compute information for proof. It generates various kinds of contracts, but also recursivity through a call graph. Now let's see how flow relies on proof to give a more precise analysis. So we've seen numerous times that flow analysis is not value dependent. In particular, it's not able to detect that a branch is dead because of some value reasoning. However, the user can inform flow analysis that a branch is dead using a pragma assert false. This assertion, like the postcondition of bad previously, is only proved when it's never reached. So proof can show that it's never actually a dead branch. When encountering such a branch, such an assertion, flow cuts the branch, so it does not flow to the subprogram exit. Other flow checks, like initialization checks, are still needed on the branch because proof might rely on them. If we take the example with the sign, the user can now inform that the else branch is actually dead. And flow will prove that sign is initialized on all paths of the subprogram, and proof, which runs later, will prove that the branch is dead. Related to the dead branches, exception handling and propagating is supported in Spark. So here we have two examples. One procedure might raise E, which might raise E condition, E exception under the count condition. This is expressed through exceptional cases contract. And then we have might raise exceptions, which might raise any exception and under any condition. Unexpected exceptions are exceptions that are raised but neither caught, neither specified in the exceptional cases. When a subprogram raises an unexpected exception, this is considered as error signaling. And like the dead branches previously, proof checks that they never happen, and flow can safely cut the branch so that it does not flow to the subprogram exit. Another imprecision of flow is on loop termination. So for for loop, which operates on a range, the proof is automatic, they terminate. However, for other loops, there is a need for a variant. So in general, a variant is a mathematical integer which strictly decreases. In Spark, it's a machine integer that either decreases or increases, and since it is bounded, there will be a stopping case. When encountering such a variant, flow assumes that the loop terminates, and proof checks the variant later. So here, we have the example. If the while loop didn't have a variant, flow would complain that it needs a variant, and when encountering the variant, it just cuts this message and let proof check the variant. Also note that there exist subprogram variants which are used to prove termination of recursive subprograms. So after presenting flow and proof and how flow computes information for proof, we now know that proof is used for more complex check that flow would be unable to prove, like dead branches or a verification of variants. It does so by leaving the check, and checks are proved later when proof runs. So this arrow is actually the other way around because it's proof helping flow analysis. However, I decided to keep it this direction because I want to emphasize the fact that this does not require the program to run twice or anything like this. Flow always runs first and then proof, and there is no additional running of the program for flow to get information from proof. What we have seen thus far is always done automatically, so be it the computation of flow for proof or the handover to proof. So now let's focus on a feature where the user can choose between flow and proof to prove the checks. It's called relaxed initialization. So we've seen throughout the presentation that flow is not value dependent. In the case of proving initialization of variables, this could represent a problem. For example, on arrays initialization, if we do initialize them using slices of the array, flow, being non-value dependent, is not able to prove that the array is entirely initialized. Also, the policy on initialization might be too constraining. So for example, if you have a record is just a structure with two fields, for example, in this case, and you try to initialize it through different subprogram calls, because of the initialization policy, X is required to be entirely initialized at the subprogram entry, which defeats the purpose of calling initialization procedures. Improvements on this area are long-standing requests by our customers. So we could think about using proof to check initialization. Indeed, proof is value dependent, and we can specify initialization status of variables using the tick initialized attribute. So if you want to state that proof is now responsible for checking initialization, as a precondition of initf1, we should say that y is initialized, and in both condition, the initialization status of x.f2 has been kept the same as the subprogram entry, but the x.f1 is now initialized. And even though it sounds good, there are lots of drawbacks. So first, no initialization policy means that the contract needs to completely describe the initialization status of variable at the subprogram boundary. Like the global contracts, it can be very cumbersome to write. And second, there is a loss in proof efficiency because the proof graph is larger. Now, proof needs to take into account the initialization of all variables when proving any contract. So we chose to let the user decide between the two. So we have now an aspect called relaxed initialization that the user can annotate on objects. as well as on subprogram parameters and function results. So if we go back to the initf1, we now specify that x is relaxed initialized, and we keep the post condition because it was correct as is. But what we gained here is that y still is subjected to the initialization policies checked by flow. When proving initialization of variables, proof considers the initialization of scalar subcomponents independently by attaching a flag, a Boolean flag, to state whether it's initialized or not. The initialized attributes evaluates all the flags recursively. So now you can call initf1, then initf2, and you'll be able to prove that y is entirely initialized after those two calls. Note that this requires no additional communication. First, there is a common routine to decide which analysis checks the initialization of variable so that no initialization check is missed. And when copying back an object subjected to the relaxed initialization policy to an object subjected to the regular flow analysis initialization policy, proves that the variable is entirely initialized. It's a design choice so that we don't have to send information to flow. Relaxed initialization is also used to annotate types. So this allows creating partially relaxed structures, and we can use type invariants or even subprogram contracts to express the initialization in a fine-grained manner. If we take an example of a stack, so we have a top field, which is a natural, representing the number of elements in the stack, and content, which is a fixed size array. And here we can see that there is no interest in initializing content components after top, because they should not be accessed. So we are able to state in the predicate that all elements between 1 and top are initialized. The rest are not. When a variable of such a type is called as an actual of a parameter, the initialization of its subcomponents is not checked on calls. They are rather checked on the direct access to the relaxed subcomponent. Even though it sounds a bit weird, if we see an example, it will make more sense. So we take the stack example, we create a value x of this stack, and we try to push a value inside the stack. At the call to push, we definitely don't want an initialization check. Rather, inside the body of push, there will be initialization checks whether when the subcomponents are accessed. This will be verified thanks to the predicate. So to conclude, we finally have a complete graph. So the Spark tool performs two analyses: data flow analysis that verifies data flow contracts and simplifying assumptions. Deductive verification is used to verify contracts and runtime checks. Following the user request, the cooperation between these two analyses has become more involved. Flow, which is faster and can see the whole program, computes information for proof. Complex checks in flow are automatically deferred to proof. And for initialization, it's possible for the user to choose between the two in a fine-grained manner. So, thank you for your attention.
Thank you very much. Questions?
So how do you make all of this concurrency safe? I mean, everything you said seems to be single process or
Absolutely.
concurrent.
So we have a very coarse handling of concurrency currently. Flow analysis checks for data races, and that's basically it. Because we do not have a model of concurrency currently that would allow us to prove more precise contracts. Yeah.
I mean, just as a plug for everything we do here, I think there's been a lot of work on how do you make these, even with rendezvous communication, all of the nice things that Ada has. I think it should be doable. I mean, with the techniques that we we've been looking at. So
Definitely.
there's something to look at, right?
Yeah, yeah.
But very interesting.
Yes.
Just continuing on that, I guess the issue is the automation, right? Because apart from the very last bit you showed, everything is fully automated in Ada, right?
It's autoactive proof, so the user can guide the provers, because usually when the context reaches a certain size, the provers get lost and choke completely on the verification conditions. But the user is able to guide the provers using either assertions, so explicit assertions within the subprogram, or it can define lemmas and call them explicitly. But yeah, so it's automatic, but when you reach a certain program complexity, it always needs the user to guide the tool.
Okay, so maybe it's not so much of a problem for the more complex stuff if it already requires.
Yeah.
So. Cool. Other questions? Yes.
So I guess maybe I missed something, but I was curious about whether there are some circularities in the reasoning, because you said flow, for instance, could maybe make an assumption that some part of the code is dead, and to get a more precise result, and then it leaves the verification of that to the prover. But maybe the prover relies on information from flow that sort of causes it to prove that code is dead, but that's actually not true. So could something like this happen? Yes.
I don't think so in this case, because when flow makes an assumption, in this case, it's always steered by the user by adding explicit assertion, stating, I want the tool to verify that the branch is dead, and influencing the checks accordingly. But there is no, let's say, flow analysis will not create an assumption out of nowhere unless it's specifically defined and flow and proof agree on the definition of such an assumption. Okay. We have actually something related to circularities, but it's more about on the subject of recursivity, when there are dependencies in the proof related to, for example, invariance or values of constant. And for this, flow is able to generate as well an augmented call graph to verify that this does not happen. But we do not have such a thing between the assumption made in flow and proof. There are those soundness arguments in the paper. Basically, since flow and proof always reason depending on what happened previously, there is no risk of trying to adding an assumption that would not be shared by the two.
Okay. Other questions? If not, I propose we thank the speaker.